Hello Math 4411 students, let's begin lesson 5, Groups of Permutations. Ever since we were introduced to the concept of groups in lesson 2, we had bits and pieces of non-abelian examples here and there. Now finally we reached a point where we have an entire lesson devoted completely to non-abelian groups. Here we go. Let X be a non-empty set. Then the set of all bijections on X forms a group under composition. It's composition, so the associativity is trivially true, and we have the identity map and inverse map. So it's a group. You can easily check that, and the detail is left to the students. Now, in a special case when X is a finite set, such a bijection is called alternatively as a permutation. And the set of all permutations on set X, given as 1 through n, is called a symmetric group of n letters. And we denote it as n. In short, here we go. Set of all bijections, set of all 1 to n onto maps from 1 through n back to 1 through n. This is our textbook's author's notation, and I'll try to follow it whenever possible, but sometimes it is more convenient to do it this way. And you can easily see the equivalence. All you have to do is replace 0 by n and vice versa. So remember the second notation as well. Exceptional cases when the second notation is more convenient, I'll just use it. Most of the time though, I'll try to follow the first notation. In any case, I was a bit premature. In any case, the order of a symmetric group is n factorial. You see, the first letter we have n choices. The second letter we have n-1 choices because 1 is already selected. Third letter we have n-2 choices because 2 letters are already selected out, and so on and so forth, and multiply them all, we have n factorial. Here's a standard notation for a permutation. 1 goes to sigma 1, 2 goes to sigma 2, 3 goes to sigma 3, and so on all the way over to n goes to sigma of n. We use this kind of notation, which looks kind of like a matrix, but this is not a matrix. It's a permutation. Some alternative notations include, like this, n-tuple, 1 through n is reshuffled into sigma of 1, comma sigma of 2, and so on and so forth. Yes, n-tuple is ordered, so this is valid expression. Or we can just list them all. 1 goes to sigma 1, 2 goes to sigma 3, like those. But whenever possible, I'll try to follow our textbook author's preferred notation, like this. You just have to get used to this. And the best way to get used to this is, of course, to use it often. Here we go. We have a couple of permutations belong to S5. So here we go. Sigma, which I'm just highlighting in blue, 1, 2, 3, 4, 5, go to 4, 2, 5, 3, and 1 respectively. And tau, which I just highlighted in green, 1, 2, 3, 4, and 5, go to 3, 4, 5, 3, 5, 4, 2, and 1, And please note that the second row covers everything from the first row and no duplicate. Same here. So we are talking about 1 to n onto maps. And determines sigma tau and tau sigma. Remember, the group operation here is composition. So sigma tau is actually sigma composition tau. So right hand side, tau comes first. So tau first, and then we have to apply sigma. Oop, wrong color. Tau first, and then sigma. Here's a typical computation. Oh yeah, right here. Composition map, so inside first, so right hand side first. And then here's typical computation. Here is typical computation. So tau first, and then sigma. So 1, 2, 3, 4, and 5 go to 3, 5, 4, 2, and 1 respectively. See this? Green first. And then let's do blue. Now, 3 goes to where? 3 goes to 5. So that's 5. Let's use color coding blue. And 4 goes where? Oh, whoa. 3 goes to 5. Next is 5. Sorry about that. 5 goes where? 5 goes to 1. And then 4 goes to 3. And then 2 goes to, 2 stays at 2. And 1 goes to 4. All correct? Yeah, all correct. And then actually we don't need this middle line as a matter of fact as a final answer. Shall I just remove them all? Yeah. 1, 2, 3, 4, and 5 go to 5, 1, 3, 2, and 4 respectively. So sigma times tau is like this, as I just highlighted in purple. Okay, how about, excuse me, right here. Okay, all right. I'll copy and paste that thing here. I don't need this. And that's all right. Okay. And highlight as purple. Okay, we have everything now. And the computation process is here. Okay, similarly, let's do tau times sigma. Again, this is computation, so right hand side first. So sigma first, and then tau. So how do you do that? So sigma first, and then tau. So sigma first. 1, 2, 3, 4, and 5 go to 4, 2, 5, 3, and 1 respectively. That follows directly from this. And then next, 4 goes to 2. And then 2 goes to 5. And then 5 goes to 1. And 3 goes to 4. And finally 1 goes to 3. Did I do this right? Let's check. Yeah, that's right. So green times blue turns out to be this one here. Let me use red. Excuse me. Copy and paste this entire thing. Okay, what do you have? Sigma tau versus tau sigma. They're different, right? They're different. So this multiplication is non-commutative. So we have an example of a non-abelian group. Here's another example. The symmetric group of 3 letters, S3, is the smallest non-abelian group, smallest in terms of the order. Let's see, if you have just 2 elements, then 2 factorial is 2, and that's going to be identical to Z2, so it's abelian. S3 consists of 6 elements, and they're all here. Identity, of course. And sigma, 1, 2, 3, I just shift 1 step to the left, 2, 3, 1, and then do it again, then I have 3, 1, 2. shift now 2 steps. So this is sigma and then another sigma. And then if I take sigma cubed, one more shifting will come back to 1, 2, 3, so you're going to get E. So sigma, sigma squared, and sigma cubed will turn out to be E. And such a thing, this thing is a 3 cycle. Sigma, sigma squared, and sigma cubed is back to E. And then tau 1 and tau 2 and tau 3 are actually 2 cycles. So 1 stays the same, and 2, 3, 1 shifting, and then shift again, we are going to come back to the original, E. And 2 stays the same, and 1, 3, switch those, and then switch again, we are going to go back to the original. And this one here, excuse me, there's a typo here. 1, 2, 3, 1, 2, 3, that can't be right. Yeah, okay. Sorry about that. That's correct now. 3 stays the same, and then 1, 2, we have the shifting there, and then shift again, you're going to go back to the original. It turns out S3 has 5 proper subgroups, and they're all cyclic. Let's see. Trivial subgroup is, of course, cyclic. And then, the first row here, sigma, sigma squared, and sigma cubed is back to E. So entire first row, that's going to be a cyclic subgroup. And then there are 3 more. Tau 1 and E, tau 2 and E, and tau 3 and E. Like this. Here, sigma cubed is back to E, and tau 1 squared is back to E, tau 2 squared is back to E, and tau 3 squared is back to E. And that's how 3 cycles and 2 cycles work. And there goes another example. Let's see, we have a couple more topics here, but not enough time. So let's stop here and let's resume 1.4 and 1.5 in the next video. Stay tuned. See you soon.